The most important contribution of van der Waals equation is it provides a very simple physical models that allow humans to understand the behavior of real gas. Back to that time, van der Waals, P ideal times V ideal is going to equals to R times T. So in this class, I will actually ignore the number of moles. Every time when I talk about the number of moles is always equals to 1. Okay, so if you encounter the situation that's actually talking about 5 moles, 10 moles of gas molecules, you start from 1, and then at the end you multiply the coefficient back. So all the V I described here is molar volumes. Van der Waals, that's actually the things I know, but the things I can measure is actually the P real, V real. These are actually things that I can actually measure. If I can actually make some corrections to my P real and the V real, so that I can actually recapture the P ideal and V ideal, then I can still use the PV equals RT equation. So he started to think about, if they have a real gas, then my gas molecules must have volume. So I know if I do some corrections for my V real, maybe I can get back to the V ideal. Since in the real gas, I know the molecule is going to have interactions. They are going to have pressures in between the molecules because they collide with each other, right? So if I can actually correct lectins, then I can bring my P real back to P ideal. Then I can actually use PV equals RT equation to do my calculation or use it to describe my real gas. Okay, so that's actually very, very simple concept. In the end, we define this. Okay, so introduce two terms. The B here has a very specific name called the excluded volume. 1 over A squared is so-called the internal pressure. So you will notice like 1 is actually minus, 1 is actually plus. So why you have all these different signs here? Okay, so let's talk about the excluded volume. So in real gas, every molecule has its own size. So the V real will be larger or smaller than the V ideal. Larger, right? Because in the beginning you say, okay, every single molecule don't have volume. And right now, every molecule has volume, so the volume you measure will be actually much bigger than your V ideal, right? So to get back to the V ideal, that's why you minus the excluded volume, right? Because we all know that this is actually big and this is actually small. Okay, so that's why you need to actually minus V to get back to the V ideal. How about P real? Is the real P going to be smaller or bigger than the P ideal? Yes, it's smaller, but why? Let me give you some pictures so that you will see why this will be the case. So this is actually one of the gas molecules. How is pressure formed? Think about if you have 1 mole of gas molecules within a container, then you will see like the gas molecules always hitting the container surface to create the pressure. If you have ideal gas, so you have the 3 other molecules surrounding by that target molecules. If you have ideal gas, there's no interaction between these two, right? So you will just hit the wall with full power. So they give you actually larger pressures. But in the real gas, you're going to have interactions between molecules. So what happens is actually all these 3 molecules, they are trying to pull that gas molecules. So in the end, this guy will hit the wall, but with much slower speed, and they will actually give you a lower pressure. This is why the P real is smaller than your P ideal. Therefore, I need to actually add in a correction term to compensate that. A is actually coefficients van der Waals created. But you will also notice that there's actually 1 over V squared. So why do we have actually 1 over V squared here? It's simply because this interaction is highly depending on the concentration or the density of molecule within the container. right? So in order to have two molecules to interact, okay, it's going to naturally proportional to 1 over v squares. So that's how van der Waals come up with this equation. Very simple, very straightforward, but that's actually the first time human can provide a very understandable mechanism to describe the behavior of real gas. With this in mind, people sometimes will write the van der Waals equation in different ways. People typically will write the P real is going to equals to RT divided by V real minus B minus A over V real square. Okay, so I guess we just put it this way, so it's easier. Okay, so this is actually another form you will commonly use, okay, for the van der Waals equation. So with these forms, you will actually quickly realize, sometimes you will see, okay, some people say, I can use an equation like this to describe the behavior of a real gas. What does this imply? Okay, so what's the difference between this equation and the original van der Waals equation? Yes, so if you see a question, okay, write down this, okay? It says, in the question it says, okay, I can describe the real gas behavior using these equations. What it really says is that the volume of the real gas can be ignored. So the volume of gas molecule can be ignored. So similar things, if I say, if I can describe a real gas system using these equations, what they are trying to tell you? Okay, the interaction between molecules can be ignored, right? Because internal pressure equals to 0. Then you go to these very specific equations. Okay, this term is 0. Then you go to this. All right, so you can consider that this and this just a special case of the van der Waals equations, right? So remember I tell you like in the beginning of the class, I said, okay, there are hundreds of thousands of equations in the PChem. There's no way you can memorize all the equations. This is actually one of the examples. These three are all equations in your textbook. Do you need to remember all three? You don't, right? You only remember the major ones. All the others just special case. Why van der Waals equation is so important? Van der Waals is actually amazing because it just provides a very simple equation with physical meanings, okay? You can actually describe to very large extents of deviations. So that's why these things is actually so powerful and famous in your PChem. Believe it or not, the van der Waals equations can even apply to conditions that's close to the liquid phase. We're going to talk about all the things later on in this chapter, still using van der Waals equations. So that's why this is actually something that's so powerful. Specifically, we're going to talk about this in chapter 6.3. And then it provides a very simple parameters, okay, and those parameters carries physical insights. For example, 1 over A squared is actually the internal pressure term, right? And then B is the excluded volume. All of things actually bring you back to the microscopic reasoning about why we see these phenomena. Okay, and then the very last one is actually van der Waals equation has been tested by so many people, and it can be validated by the experimental results. Let's talk about the drawback of van der Waals equation. The drawback of van der Waals equation is that, yes, it can actually describe pretty well for the real gas behavior, but sometimes it's not super accurate. You will still tell you all the trends without any problem, but the absolute values you calculate from the van der Waals equation, it deviates. At the van der Waals, there are so many scientists trying to modify the van der Waals equation. So on the top is actually two improved van der Waals equations. The first one is actually called the Reddish-Kwong equations. But if you look at this equation carefully, you will see that it's actually very similar to the van der Waals equation, right? It always starts from the P in the correction terms, V in the correction terms equals to RT. Hayes-Robinson equation is actually another one, but you can still see that P in the correction terms plus V in the correction terms equals to RT. You need to memorize these two equations. You don't. Okay, so don't waste your time. Memorize this. Okay. For this type of equation, I will give you. Okay, if I want to test you about whether you understand this concept, I will just give it to you. Okay, very likely. Okay, I will say, okay, compare the van der Waals equations, Reddish-Kwong equations, Hayes-Robinson's equations at different temperature regimes. Which one is actually more accurate? Under the case, all the things you memorize is actually the van der Waals equation. All the other equations, I will give it to you. Okay, but you need to know how you actually apply this equation to produce the plot they want to see. So you will know which one is actually closer to the real gas conditions.